There's another one crucial problem that I would like to review with you. It's the knapsack problem. You have a knapsack with capacity W and a bunch of items that have value and weight. You need to maximize the value with total weight less or equal than the capacity of knapsack. If you are going to address this problem with naive solution, then the complexity will be 2 powered by n. And for real-life problem this complexity is too big. If we will have 40 items to choose from, we will need to do around trillion function calls. So let's try to address this problem via dynamic programming. We will start with building the table. Imagine that the capacity of the backpack is 5 and you have items with value 5, 11, 17 and the weight 1, 2 and 3. The row for the table will be the items and columns will be the weight until the maximum weight. This problem shares some concepts that we previously learned in the coin change problem, and you will see why in a few minutes. Let's start with the base case. How much value can we take from the weight 0? It's 0, so we need to fill all the rows with zeros. And if you have an item with 0 value, it doesn't matter how big your backpack is, because it still will be 0. So let's fill all the columns with zeros. For row 1 and column 1, the first thing that we need to check is, can we fit the current item into this cell? For this we need to check if the current item weight less or equal than the current capacity, which is represented by column. We know that the first item has weight 1 and we are doing math for weight 1, so we can fit that element into the cell. Next thing that we need to do is to use previous calculations to solve this particular sub-problem. We need to decide whether we should take this item or not. To make this decision we need to take a previous item, which is pretty easy, it's row -1. And the second thing is we need to take the previous result with weight that is enough to fit the current item, it's row -1 and the column minus weight of current item, which is also 1. Now let's move to the column 2. First thing first, let's check if we can fit that element. 1 is less than 2, so it's fine. Next we will check previous item and previous calculations. And let's fill this row until the end. The result will always be 5, because no matter how much weight we can carry, if we have one item with weight 1, the result will be 5. For row 2 and column 1 we need to check weight. And as we can see, 2 is more than 1, so we have only one option to not take this item into consideration. We will only copy the result from previous row. Let's move to column 2. As we can see, current capacity is 2, is equal to weight of item, so we can do the math here. Try not to take an item, look at the previous row, or try to fit it. Look at the previous row and column minus current weight and add 11. So we have possible results 5 and 11. 11 is bigger, so let's write the result. For column 3 we need to check the weight, looks okay. Now let's do the math. Look at the previous row, or look at the previous row and column minus current weight and add 11. The result is 5 and 16. Let's write down the answer. So let's take a moment and write down the formula that is going to be applied for each cell. If column is more or equal than weight row -1, then for table row column we take the maximum from table row -1 column, and from table row -1 column minus weights row -1. Else we take table row -1 column and fill the row until the end, because the answer will not change. Let's move to row 3. We will fill the value until column 3. Now let's check weight. Do the math. Can we take 16 or 0 plus 17? We take 17. For column 4 we will take 16 or 5 plus 17. This cell is 23. For column 5 we will take 16 or 11 plus 17. So the answer is 28. Now let's jump into implementation. First thing first, we need to initialize our table with size of weights plus 1 for rows and max weight plus 1 for columns. Since we are going to utilize zeros for base cases, we are going to iterate from 1 to the size of weights for rows and from 1 to max weights for columns. Then we are going to apply the formula. If the column is more or equal than current element, that means that we can fit the element, so we should decide what is a bigger value, with this element or without it. If we can't fit this element, then we just take case without it. And as a result, we just going to return the last cell. The time complexity of optimized solution is O n by m, where n is possible weights and m is max weight. The same for memory.